So with that, this is the start of the big section and really the most important part, I'd say, of our session today, especially if you don't have much experience on construction sites, where we're going to go through all these different practices that DOT wants to see on their sites, and which mainly have been proven to really work well in keeping sediment on the project. So again, that's me. You've already seen the picture. So we have this toolbox, and we tend to go back to these same tools over and over again because they've been proven over years to work fairly well. Every project has an erosion and sediment control plan, which we've mentioned earlier. And as part of that plan, there's a key, which you see here, which shows all the different practices that will be on that project. Notice all the symbology. So these symbols are used on all DOT projects, and once you're reading these plans fairly frequently, you don't need to go back to this key and find out what that symbol means. But these are all the different practices that may be seen on a given project. So this is your key that's in your plans. So we're going to talk about things you do at the beginning, and then we're going to move to the perimeter and then to the interior of the project as we talk about different practices. All right, so right on the outside of the project is an entrance, and this entrance is intended to reduce mud from getting out on the street. As I mentioned earlier, that's a big problem. It causes a lot of headaches and a lot of fines when that happens. So it's constructed of a geotextile laid down on the ground, and then the Class A stone, which is the smaller of the two stones that we talk about, and it requires routine maintenance. So that is, if there is mud that gets collected there, then you have to remove the rocks and the mud and place some more stone there. We want to have it at least 50 feet long, so there's enough time for the tires to rotate and knock that mud off. All right, and so this is where I'm going to try my technology here and see if I can, I need to stop sharing, and then I need to share again. And I'm going to share this little movie. So this is what we'd be doing if we were actually out of the field. All right, so we're looking at a construction entrance pad. Remember from class, the key features are they need to be at least 50 feet long, 12 feet wide, have to be flared out by the road, and we have to have 8 inches of Class A rock. As you can see here, not the large rock, but the smaller of the two rocks we talk about, 3 to 5 inches in size. And we need to have a geotextile material underneath the rock. If you don't do that, then generally the rock is just going to get pushed down into the soil. So we want to have something underneath the rock. What is the purpose? Well, we're trying to vibrate those tires to knock off the mud before the truck gets onto the road. We don't want to see any mud getting out on the road. That's a sure way to get a violation. The public doesn't like to see that. Now, there's some alternatives to this type of entrance. There are some commercial products, such as those that are made of corrugated metal. They also vibrate the tires as the vehicles are moving out onto the road. There are some that are based on cross ties. Those are used in forestry frequently. And then kind of scaling it up a little bit, we can actually park somebody with a pressure washer out here, and they can wash those tires individually. Those are cases where we really want to make sure there's not any tracking out onto the road. And then lastly, The most expensive system, but also probably the most effective, are these commercial wheel washing stations that go in right by the roadside, and as the truck pulls through it, pressure washers get the undercarriage, they get the wheels, and are very effective. Generally, people are using those in very tight situations where they don't have room for something like this. Either way, again, make sure that you have some system in place to get the mud off the tires of the vehicles before they get out onto the public roads. All right, well, hopefully everybody got that. So now I got to reshare back to our presentation. All right, so all through this section on BMPs, you're going to see these nice colored diagrams. And they're also available, we'll talk about, well, I guess we're not today, but they're available online where you can find a whole book of these BMPs and all this information. But here you can see we've got the indication of the 8-inch depth, the Class A stone, 12 feet by 50 feet, and the flare, as you see here, so the rear tires don't end up back in the mud. And then I mentioned the pressure washers. So here's the manual pressure washer. Poor guy has to sit here all day and wash wheels. And then the automatic system on the left, which is again very effective. I think one of these units might cost a couple $100,000. So you generally don't see them except on, say, a mining operation or someplace where they're going to be there for years and years. But they can be used. All right, so the other thing that goes in when we're starting a project is the safety fence and flagging. So there's a couple of reasons why we have that. You see the orange fence down here, and that is, first of all, to keep the equipment operators on the project and not out in the wetlands or private property. It also helps to keep people who are coming from outside the project from walking onto the project as well. So we put those out before we disturb the lands. We want to make sure that we've delineated the project boundaries before all the operators get out there. You follow the contours. You can use wood or steel posts. Most of our practices, we want steel posts, but this is a case where it's just there as a warning, so it's not a structural item. Again, to these colorized diagrams, you see the 5-foot post. It's 2 feet in the ground, and the visible fencing attached to it. We can have a spacing of 10 feet here, so that's way bigger than we normally have for, say, silt fence or other practices. So these are just some of the indications of the types of systems you want to put out on the boundary. You may also be able to use jurisdictional flagging, and we say jurisdictional because generally this is what's used to indicate areas of disturbance inside of, say, a wetland or a stream buffer, areas that you normally would not want to see equipment operating or people operating. And if you have a permit from one of those many agencies to get in there, then you can put out these stakes and indicate where the boundaries are. And you can see 25 feet apart. They just have to be visible. So you don't have to pound them in as much because they're not structural. They're just a kind of a marker. So here's some examples of places where you might see these things. So here we have a riparian buffer zone. So those are areas around a stream that you're needing a permit to enter and disturb. So we've got 2 zones in those, a zone 1, zone 2, and different things can happen in those zones. So they may have flagging and indications to show you where those zones are. But here you can see this is the right-of-way. So all these diagrams, you're going to see this is the right-of-way for the highway. And obviously we're crossing the stream right there. And then we've got the stake line for the fill slope. So this is a fill area, and you can see that right here. And then also the safety fence, which is put in to make sure people don't get off the project there. And then the flagging that goes this way. Again, keep the operators that are over here from getting down in towards the stream where they might disturb an area that's not allowed to be disturbed. Here's an example of a stream that does not have the same type of zones around it. This is all environmentally sensitive, and so we're going to put the flagging on both sides to keep the equipment out. Again, you see the fill line, so that's the flagging that'll show the operators where they can add soil to build up the highway to go over this stream. And there's our right-of-way and our easement and safety fence right there, and safety fence down here, again to delineate where the project is. Now here's an area where we're allowed to do some disturbance. So here's our right-of-way going on either side. We got our fill boundary over here, and then over here, see, this is a wetland that's mapped out, and we're going to be allowed to do some fill in the wetland. Okay, so that means we got a permit to do that. And so here's our flagging that's going to go along through there. And then we also have the safety fence on the outside to keep the operator from going any further. And in this little zone right here, we're allowed to have mechanized clearing, which means we're allowed to get equipment in there and cut down trees, etc. And this is a sort of a contrast to that. Very similar situation. We got a wetland that we need to get over, and so we're going to have some allowable hand clearing right there and right there. So you can see we're putting the safety fence around the hand clearing area, got the flagging in for the fill, and we got the flagging for the inside of the wetland. So these are all indications of what kind of work you can do in different parts of the project. And especially when you get around water, then you really have to pay attention. So again, here's a stream that does not have any kind of a buffer zone around it. And maybe it's an intermittent stream, for instance. And so we got flagging that's going right up near it, so we can get our equipment right up close to it, but not in it. And that's where we need to stop right there. And then out over here, we've got some drainage easements. This is where you're going to put this stream into a pipe, for instance, and the pipe's going to extend out this far. So that's going to be an easement that the department's going to get in order to put that in. So here, if you have eyes probably better than mine, you can see the flagging out here. And this is a good example of a wetland. And so they've put in their flagging. Maybe this is where the bridge supports are going to go. I don't know exactly for this particular project, but it just gives you an idea of what you're looking at. And then we got the safety fence, of course, right on the border as well. Okay, so we're kind of moving into the project now. We're underway doing massive grading, and we're looking at different types of systems to get water where we want it, basically. So in this case, we're going to slow the water down with a silt fence. So we've got small areas that drain to these silt fences, and we shouldn't see a lot of area. So just small edges that maybe aren't draining into a sediment basin. So these are, whoops. These are usually on the edge of the project. They may be a safety fence on the other side of it, but they should be set up so that they pool the water and drop out sediment. So we want to make sure that they're buried at the bottom so water can't get underneath them. So here's a diagram looking straight on. We have a steel post, and the steel post has to be 2 feet in the ground and generally 3 feet above ground. So 5-foot posts are the standard. They can be spaced 6 feet apart if there's no wire backing. That's what this mesh is here. And they can be 8 feet apart if you do have that hog wire backing. And so we're going to have 2 feet of silt fence above ground and 1 foot buried in the ground. Got zip ties that are used to hold it to the posts, and make sure that they are the UV stabilized zip ties. If you use a indoor type of zip tie, then they will degrade very quickly in the sunlight. So this is probably the most critical part of a silt fence, and that is getting that flap on the bottom buried correctly. So here we've got the material. It goes down about 8 inches, and then we have it go horizontally about 4 inches. Okay, and then we pack the soil down, pack it hard. We may run a wheel over it or something to pack this down, because we want to make sure that it is firm enough so that when the water builds up on the fence, that it's not going to pull this out and the water go under the fence. Okay, very important. There are machines that do this, actually, in clear areas anyway, that you can put on the back of a tractor. So this is what they should be looking like when they're installed and functioning properly. You see how we've got pooled water and it's slowly leaking through the fabric. So the fabric is supposed to be leaky, but not very leaky. It's just enough so water will slowly leave after dropping out the heavier sediment. So a couple of things we need to remember with these. As with all our measures, we have to make sure that we maintain them. So here's a case where this sediment fence or silt fence is about half full of sediment, and that's the point where you need to start removing sediment. And it's same for all our other practices. Once they're about half full, it's time to get a grader over there, a backhoe, and dig that out or install something else. We also never want to see concentrated flow hitting a silt fence. So this is actually a case where the flow was going over here, and they moved some materials, and next thing you know, it's coming here right to the silt fence. And even though this was a hog wire backed silt fence, it got knocked down. And so all this sediment now may be leaving your project and into the wetland, as we showed earlier. So avoid any kind of concentrated flow on a silt fence. And here's a case where the silt fence was not buried correctly, and so we had blowouts here and there, and as a result we have concentrated flow, and so now we've got gullies forming on the downhill side. So this is why we need to be really careful about how we bury that fabric. Over time, these silt fence materials do break down, and you can see this one starting to fray. Probably some kind of equipment came along and tore this out. And once this happens, this silt fence is no longer working at all. It's actually just collecting the water and sending it in a concentrated flow out right here. So this is going to have to be replaced. And so people are going to have to pay attention when they're inspecting these devices, that there's no tears, that it's not starting to fall apart, etc. So the main function of a silt fence is to do what? Pool water, drop sediment, release slowly, filter runoff, direct flows to basins, prevent landslides. Okay, well, hopefully you've heard me say this enough, and we're talking about pooling the water and then slowly releasing it. Now, we can have big storms that come along, and our silt fence may get overtopped, even though it may have been placed correctly and without a lot of land draining to it. So how do we prevent this? Well, one thing we can do is install an outlet. So as you see here, we have the silt fence, and then we have a break in the silt fence. And what we've installed here is hardware cloth, and we'll talk more about that in a minute. And then we put our stone, washed gravel, we call it 57 stone, right here in front of it. And this allows the water to leave without overtopping. It's because the water will leave through these rocks much faster than through the fabric. So it's sort of a release mechanism. This should be placed either near the bottom or at the bottom of this slope. So this is the low point on the silt fence, or it could be a little bit upstream so you get some pooling, but generally people are putting these in the low point. So here we have the hardware cloth I talked about, so 1/4 inch wire mesh, and should be galvanized. We've got stakes that are on 3 feet, So we had 6 and 8 feet for the silt fence. We had 10 feet for the perimeter fence. So now we're down to 3 feet because this can get a lot of flow. And so we've got the rock on it and we could have a lot of pressure. So we're going to have 3-foot spacings. Make sure that we overlap the rock onto the silt fence so water doesn't get around it. We're driving those stakes in 2 feet and making sure that the wire is properly supported again with zip ties. And a cutaway is mostly showing us this should be at least a foot of stone. And you can see 2-to-1 slope, but mostly get at least a foot up there on that hardware cloth because the hardware cloth isn't going to slow the water down. You need the stone for that. All right, so here's a movie that kind of shows you one in action. So there's our silt fence release mechanism. We actually have a slope drain that's being released right there. You can see what's happening here. We're cooling a little bit, but not as much as we would have if we had the silt fence there and releasing the water. This isn't exactly cleaned up pure water. That's typical of what we're releasing. It's going to look turbid when we drop down the heavy silt. All right, there's another silt fence break right there. Now there's an alternative we have to those stone outlets, and that is using a wattle. And this, I think it's the first time we've talked about wattles, so I put in a picture here if you're not familiar. This is a coconut or coir wattle, and so it's made up of coconut fiber, very tough, lasts a long time in the field. And we can put these in place of that stone and hardware cloth fence. So we're going to put these stakes along both sides. So you can see there's a stake on the uphill side, stake on the downhill side, and make sure we staple the bottom of this in. So we have landscape staples that are going to go through the mesh and hold it down, and then we have at least a foot of the wattle going on each side so that we don't have water getting around it at the silt points or silt fence. So here's some more examples. Close up here of the installation. So you see how we put stakes on both sides at an angle. We're trying to force that wattle down to the ground. So that's what these are doing. They're kind of holding it down to the ground so water can't get underneath it. And then to double down on that, we are stapling through that mesh, again holding that bottom close to the ground so water can't get underneath it. All right, so we just talked about this silt fence break, and we have another device that's exactly the same except there's no silt fence. So this is called a special sediment control fence. It is usually used where you have expected high flows and a silt fence might not be able to handle it. So as you can see, this is a jurisdictional area, as was mentioned up here. So it's a wetland. We can't put in, let's say, a sediment basin here because of you can see the high groundwater would mean that would just end up being a pool. So instead, there's a special sediment fence that's been put in. So these are very effective. They're expensive, obviously, compared to a silt fence, but where we need to really control the sediment and we don't have any other options, this is one way to do it. So everything else is pretty much the same we just talked about with the silt fence outlet. So we got 3-foot spacing, the quarter inch hardware cloth, and the 1 foot of stone. And I mentioned this stone, it always should be washed 57 or number 5 gravel. So if it's not washed, then what happens is the first storm hits it and it washes out all the fines and you get this big plume of white material that's very obvious. Instead of those special sediment fences, we can also put in these. This is also a substitute for a silt fence. It's a wattle barrier, so it's that same coconut fiber wattle that is staked in so that it's held down and stapled in. So again, this is only for very small areas. You don't want to see a lot of flow coming to these. So just sheet flow coming from an adjacent area. And here's a bird's eye view looking down. And again, we've got the overlap here. Typically, these are anywhere from 12 to 18 inches in size. They come in a lot of different diameters, but mostly we're using at least 1 foot diameter. And there's our staking pattern. And again, seen this picture before, we want to make sure we staple to get that thing tight to the ground. So here's an example of an installation next to a slope. So instead of a silt fence or a special sediment control fence, we've put in these wattles. All right, so now getting water where we want it on the project is very important. Generally, we're going to try to capture the water and get it usually into some kind of a sediment control practice, a sediment basin or some other structure that will drop out the sediment before we discharge. So we have a temporary diversion, as you see here, that's catching water before it gets off the project and sends it through a treatment system of some kind. So this is the diagram, pretty simple concept here, and a cutaway where we're cutting here and putting the fill material over here and taking the water somewhere down where it will get treated before it leaves the project. We have a temporary silt ditch, very similar to the diversion. The diversion can be pretty much anywhere. These are usually on the perimeter. Notice we have check dams. We'll talk about check dams in a little bit, but they're put in to keep the water from flowing too fast and starting to erode these diversions. And this diagram should look pretty familiar. And here's our cutaway. One thing we'll talk about when we talk about vegetation and ground covers is that these are areas that have a lot of potential for sediment getting into water because we're concentrating it and sending it into a basin. So we want to make sure that it's covered up with grass. So all these diversions need to be grassed very quickly after they're established. All right, so we also have an earth berm. So this is basically a block, a dam to keep the water from going somewhere. In this case, you can see it's a small slope, but we're trying to keep the water off this slope. And we'll talk about slope drains in just a minute, but that's what these berms are all about, trying to keep water off slopes. So again, we're going to want to grass them, make sure that any area that's handling water is grassed so it's not contributing to the sediment load. So I mentioned the slope drains, so some good examples here. We've got the established road bed. We've already got our grade on these slopes. We don't want to have water running down those slopes because it'll create rills and gullies. So we're going to capture all the water up on the road bed and send it down safely in these little pipes. 12-inch corrugated pipe is the usual type of material we're using here, and then release it safely at the bottom. So in this case, you can see over here we've got these check dams, these rock check dams, and they're releasing it right onto the check dam. So there's no erosion at the end of this pipe. So you got to make sure at the end of the pipe you have a non-erosive release mechanism. You may have to put a pad down of some rock and geotextile, but in this case, if you've got an existing structure, you can use that. That's very common. So up on that road bed, trying to capture the water and get it into the pipe is really important. So if you look here, again, this is a bird's eye view looking down. So the flow is coming this way. A couple of things to notice here. We've dug out a hole here. It's kind of hard to see, but this is a sump. So this has been over excavated so that the pipe is actually above ground. We've also put in a berm here, or a kind of a speed bump. And what this does is it makes sure the water doesn't bypass this. Sometimes water goes around it, and we end up with a lot of water in one slope drain instead of a lot of slope drains. So this is sort of it looks like a speed bump. And there we capture the water and we send it through the berm that we've established down the slope, and there you can see we release it onto a stabilized outlet. Upper right, this insert, this is normal. We normally will put a rock barrier around the inlet to prevent a lot of heavy sediment from getting into the pipe. And we'll talk about these inlet protection systems in just a minute. And sort of a 3D view of the same thing. We just saw that we're coming into the sump here, and so this is going to settle some sediment before it gets into the pipe and then down onto the rock pad. So this is why you need to be really careful about what happens at the end of the pipe and not just up at the inlet. So here's a couple of cases where the pipe just was not extended all the way to the bottom of the slope. The water was released, and you can see what's happening. We're getting major erosion down at the bottom. So let's think about these slope drains and what they actually do. So are they there for sediment control, to get the water to the bottom of the slope, get moisture out of the road, block unauthorized traffic? Okay, so we are just trying to get water down the slope safely without eroding the slope. Okay, so we've talked about our ditches. Now, what are we going to do in the ditches and around our outlets to protect those? So let's talk about that. I mentioned the check dams. So check dams, they call them check dams because they check the flow. They hold it up and keep it from getting too fast and erosive. So that's what these wattles are used for. They're check dams, essentially. So on the left, you can see that's a coconut fiber. Hopefully by now you can recognize that that's a coconut fiber or coir wattle. And on the right, these are made of excelsior, which is a curled wood fiber. So they take aspen and take shavings off of it and put it into a blanket, as you see here, or into a sausage casing or whatever, and make it into a wattle. So in these two cases, in this case, we've got a blanket that's been put down in the whole ditch line. And in that case, that's fine. We put the wattle right on top of that. In this case, we don't have lining. And so we have to put a blanket underneath this wattle, because when the water starts to flow, it may come over top of this. And if it does, it would erode on the downhill side. So we need to protect the ditch from erosion. So if there's no lining, then you have to put down a lining underneath each of these wattles. So here's a 3D diagram, and you can kind of see the blanket that's been put down, and we got the stakes. Also note that we want to make sure that these ends are all the way up and we don't have any chance of water getting around the check dam. And that's true for all check dams. So the wattles, we've got the stakes. We've already talked about this when we use them as an alternative to a silt fence. And we haven't talked much about this, but we can add that polyacrylamide that I mentioned earlier as a powder to the top of these wattles and then on both sides on the blanket. And what that does is it releases some of this flocculant or polyacrylamide into the water as it's running down through the ditch. And as a result, we can reduce our turbidity with that chemical treatment. So that's very common on a lot of the DOT projects. You'll see that we are putting out the flocculant on all the check dams. Bird's eye view, again, you see the blanket, and we've got flocculant on the blanket. That's because sometimes the flow is actually right through the material in the wattle. So if it goes through, then it doesn't contact this material up here. So you want to put it on both sides. All right, so we take a cup of this, or half a cup, and we put half of it on the wattle, and we put the other half on both sides. So that way we get good treatment. And one more diagram to make sure you got this down. With our wattle, good contact, make sure that there are no gaps under here. Otherwise the water will just jet through there and erode the ditch. So no gaps underneath the wattle, and we've got treatment of the polyacrylamide right there. And notice how we got the wattle going all the way up with a low point in the middle. So that makes sure the flow goes right there where we want it. And here's a picture of what we just talked about. So there's our half a cup of PAM, about 4 ounces. And I guess that's actually yeah. So then we've got 2 ounces on the surface. You see the powder there, and 1 ounce on the blanket, both sides. So we're going to apply this after we have significant rainfall. I think this should be a 1-inch rainfall here. I haven't changed that, but the key is when you inspect all these devices, if you don't see the material, once it gets wet, it turns into a jelly. And once you don't see that anymore, then you need to put some out. There are different forms other than the powder that you see and we've been talking about. There are flock logs or solid blocks of flocculant, and we don't usually use these on DOT projects as far as I know. They have been used, they have their purposes. They don't work really well in open ditches. There's socks full of a different chemical called chitosan, and these are used a lot on the West Coast instead of polyacrylamide, and won't get into all the reasons behind that. Then we have these tablets that some call fizzy tabs. They're actually this powder with some bicarbonate added so that they actually fizz just like Alka-Seltzer. That helps the powder dissolve faster, and so that's another alternative. So what's actually happening here? Well, we're taking these fine particles and gluing them together with the polyacrylamide or any other flocculant material, and as a result we get these flocks that are like, they're not quite as dense as sand, but they're the size of sand. And so you can see up here on the left, we've treated it with treated this turbid water, and so now we've got all these little flocks that have settled out. You can see how clear the water has gotten compared to where we don't have treatment. So this is a pretty well proven technology, works really well if it's done right. So there's sometimes we want to have rock check dams because of expected high flows, and in those cases you may not have the wattles, but if you still want to do the treatment, then you can add a blanket, as you see here, and this is the symbol over here on your plan, and then put that polyacrylamide on the blanket itself, and so we'll still get the treatment. Rocks are not a great place to put polyacrylamide. The granules tend to just fall through the rocks and end up in the bottom, and we don't get very good treatment. All right, so here's a video. Again, if we were in the field today, you'd be seeing this live, but this will show you an example of how this works. So we have this ditch line that we can install practices in and send some muddy water in, and that's what you're seeing here. And we put polyacrylamide on each of these wattles. So now you're going to get a look at what it looks like at the beginning and the end of this treatment. All right. So more on this polyacrylamide. I mentioned that it turns into a little bit of a jelly, as you see here. And that's what it should look like after a rainfall. Notice here that the water is very clear. And I can tell you from experience that the only way this water is as clear as this after a storm is if it's been treated with polyacrylamide. Now here's an example of why we put the polyacrylamide also on the blanket. So here you can see the kind of whitish gray jelly that the material turned into after a rainfall event, but there was not any PAM put on the blanket. So here the water's going through the wattle, so it's not touching any of this polyacrylamide up here, and that's why you see the water is the same color on the downhill side, because it's not getting any treatment. So that's a good example of why you want to put it on the blanket as well as on the wattle. All right, now to the big gun rock check dams. So where we've got higher flows, we expect our Type A rock silt check is shown here. It has the larger stone, the Class B riprap. Okay, so that can be I think 5 to 12 inches or 5 to 10 inches. It's a large rock, and that's the structure. It sort of holds the structure of the check dam. And then on the front of it, we'll put a face of that 57 washed gravel. And what that does is it restricts flow, so the water does get slowed up and does not build up a lot of energy to erode that ditch. All right, so that's our rock silt check Type A with, remember, the B stone and the 57. So different views. We got the front view of the check dam, and notice how it's really important we have a low point in the middle. If we don't have that low point, then we don't get flow that is actually going through the middle, which is what we want. Okay, so I had a question about the polyacrylamide, so I'll back up. As far as, well, let's go to this slide. The question was, do you have to apply this during a project more than once? And the answer is yes. You're probably going to need to apply it many times. Every time it rains, every time you have flow, some of the polyacrylamide is going to disappear. So as you're inspecting all these devices, you need to be looking to see if it's there, and if it's not, then you need to add some more. So I hope I answered that question. So again, low point so that the water goes through the middle and not around it. And then we've got a face of 57 stone, 12 inches in depth. So the flow is going to come this way and slow up as it hits that 57 stone. Some people call this filter stone. I don't like to call it that because it doesn't actually do any filtering. It just slows the flow. And we already talked about how if you want to do that polyacrylamide treatment, you need to put a blanket on the front face. So this is a good example here, and put the PAM on the blanket. The granules will stick to this blanket very well. They don't stick to the rock very well. Does anybody see anything wrong with this check dam? If we were in class, I'd hope to see a lot of hands. Notice how it's flat. It should not be flat. This should be a low point right here. Maybe a little bit low, but it's not very low. It needs to be pretty clear. And so here's a diagram of a Type A check dam with that blanket on it. And you can see the stone to hold the blanket in place. Obviously, there's no place to staple it, so you need to just hold it in place with some rocks, as is shown here, these rocks. All right, so here's another one of those Type A dams with the Excelsior blanket on it. And here you can barely make out, but there's a little bit of PAM up here. I don't see any down here. So if you're doing this inspection, again, we need it on the blanket and we need it distributed so that as the flow goes through, no matter how high or low, it's going to get some treatment. And this is another example of a check dam that does not appear to have a low point in the middle. So a very common problem that we see. People think dam and they think it's got to be level, but no, it needs to have a low point in the middle. All right, so the Type B also uses the Class B stone, but we don't have the 57 stone. And these are usually used in very low flow, low slope types of ditches where we don't expect to see a lot of erosion anyway. So they will slow the flow a little bit, but not a lot. Routine maintenance. So we've talked about before, anytime even these things fill up halfway with sediment, which they will, then you need to dig that sediment out. So here's a cutaway of that Type B, which is just the Class B stone. This diagram shows a tail on it, which is a good practice if you can do it, because as the flow comes over, it may be erosive if it hits this backside. And so if you can dissipate the energy with a tail, that's a good practice. All right, so the purpose of a check dam is to settle sediment, filter the runoff, slow flow to prevent erosion, or to stabilize the ditch sides. All right, hopefully everybody's got this idea now that we're just trying to slow the flow. Now, we will settle some sediment, but that's not the purpose. We also have a clear water diversion, a relatively new practice and really an excellent practice we have on DOT projects. So basically the concept is we've got clean water coming out of, let's say, an adjacent wooded area that is heading towards our project. Well, two reasons why we don't want it to get on the project. One is it's clean, and once it gets on the project, it won't be clean anymore. And secondly, we don't want to have to handle out here on our project all the water coming off the adjacent area. So we line a ditch. So you notice how we've got some kind of a plastic or geotextile lining, and when the water gets into the ditch, it's taken directly to a stream because it's not been interacting with our project, so it should be clean and we can send it right to the stream. There's usually some kind of a check dam down at the end, but it should remain clean. So any excavated areas around that need to be grassed. Again, on the perimeters, anytime we have water flowing, we need to have grass as soon as possible. Okay, so we saw that slide in the very beginning talking about what happens when sediment gets into pipes. And that could be storm drains, it could be culverts, and we're going to need to try to do something to keep that from happening. So we have some options for inlets to storm drains, and we also have some options for culverts. So essentially we're going to put up a stone barrier, and I hope everybody understands by now the stone is there to slow the flow. All right, so all it does is slow the flow, and then we get the heavy sediment to settle around it, and then we get just muddy but not heavy sediment water into that storm drain. That keeps the mud from accumulating in the storm drain. So we have three types of devices for these storm drain systems that we've installed. One is a type A, and the type A uses the big stone, the class B, along with the 57 or number 5 on the face of it. And these are typically located far from any traffic because they're big devices. If someone loses control and goes off into our project, they could do a lot of damage to their car. So we keep that far away from traffic. We got the type B, which is pretty much the same thing, but we're using the type A stone, smaller stone. So we're not expecting quite as much flow there, and we can be closer to the travel lane as well. And then real common is the type C, where we don't have the structural stone that we see here, but instead we have that hardware cloth supported by steel stakes. And it's just basically that silt fence outlet or the special sediment control fence encircling a storm drain. So bird's eye view and cutaway of the type A. We do tend to want to have 1.5 feet of space between the rocks and the inlet itself. And that's generally just to keep the rocks from falling in when they're installing it or during heavy storm events. Excuse me. So that's for all three of the devices. And you can see the dimensions here. Nobody's going to be measuring these, but generally that's what we're looking for, about 7 or 8 feet. Type B is same thing, smaller, so you can see 5 foot, and we've got the smaller stone as well. Just a side note, the aerial view shows the grate in the storm drain, and this view shows no grate. And personally, I would like to see that grate in there 100% of the time, because it's a safety issue to have that open gaping hole there. And then we have the type C, which we talked about and saw the picture, where we're encircling a storm drain with that hardware cloth and the 57 stone up on the hardware cloth. Guess how deep it would be? Hopefully everybody said a foot. So you need to have at least a foot of stone. Now, if you happen to have a storm drain that's in let's say a swale in between two lanes of highway, and the flow is coming this way, we know there's not much flow that's going to come from other directions. So you can actually open this up and essentially put in a check dam made up of this hardware cloth and the stone. So this diagram shows you just got a barrier on one side before the flow gets into the storm drain. So those are a couple of options for installing the Type C storm drain protection. Culverts are the same thing. We don't want to see a lot of sediment settling in there, so we're going to put a couple of types of barriers there, a Type A or a Type B, and the difference is the size of the stone and the size of the drainage area. So starting with the Type A, we've got the Class B stone, and then the 57 stone on top of that. Notice how we have a sort of an excavated area. I can back up to this picture. This is where the sediment's going to settle. So you want to have an area around it that will allow the sediment to settle as the flow is slowed with that 57 stone. All right, and then our Type B, not much difference except for the size of the structural stone that holds the 57 stone. So this would be a smaller drainage area that someone calculated before they put it on the plan. All right, so we have another type of inlet protection, and that is once you have the road paved, you may need to protect the inlet still if we're, say, still working the soil and there might be some sediment getting out into the roadway. And a couple of ideas behind these, there's lots of different devices. This is one that is designed to be underneath the drain, or actually it's on top of the drain, but it's blocking flow through with some fabric, and then it's got the little barrier there. And there are some that actually are inserted underneath this grate that catch the sediment as it flows down through the grate. And here's one that actually blocks the flow. It just forms a dam, and then once it builds up enough, it'll go through those gaping holes there. So that's a barrier system. Some people don't like this as much, or either of these actually, because they push water out into the roadway. And if that's a live traffic zone, then that could be a hazard. Obviously, you need to have your device installed to have it actually working. All right, so we've talked about all the other aspects of controlling water and getting it where we want it, and maybe slowing it up and pooling it. Now we're going to talk about how we're actually going to trap sediment on purpose. So we have a whole bunch of different devices and systems for doing this. The oldest and I'd say more primitive of the devices is the Silt Basin Type D, which you see here. They should be used generally in very short types of projects that don't have a lot of exposure or don't have a lot of time where there's exposed soil, because they don't work really well, but they're usually better than nothing. You can see in this case, both of them were actually put in the ditch line. So bird's eye view, we're looking at generally these devices, all these settling devices, we want to have the length twice the width. So sometimes it could be longer, but that's a common engineering term that you want a 2-to-1 or greater settling area. So again, this is in the ditch line. We can actually have a steep slope on these because we have limited area. Generally, we don't want to see more than a 2-to-1 slope, but we're allowed to have a little bit steeper slopes with these devices because they're short term and with limited space. Now this is what I would call our workhorse device, the skimmer basin. So the skimmer actually functions to slowly dewater these basins. So picture on the right, we've got a full basin. You can barely make out right there, there's a skimmer, and it's slowly going to drain down. This is the skimmer after a storm event. You see the pipe through the dam. So as the skimmer floats up, as the basin fills up, it will get water going through this pipe and out through the dam. So it has to be floating above the level of this pipe in order to actually have water leaving it. So a lot of different concepts behind a skimmer basin, and we'll talk about these baffles as well when we get to some of those other fine features of these basins. So this is a very effective system. These are very complicated looking diagrams, but after a while you'll realize there's some real basic features like bringing the water in safely so it doesn't erode the inlet. In this case, we put it in one of those 12-inch corrugated pipes. Otherwise, we could line this area so that it didn't erode. There's some other options. We've got our baffles that we'll talk about, and here's our skimmer. We also have, you see here at the bottom, a pile of rocks, as we saw here. And the reason we do that is to prevent the skimmer from coming all the way down into contact with the bottom. Picture the bottom of these sediment basins being pretty muddy, and that soil can be pretty sticky. So it may actually hold on to this floating skimmer and keep it from floating up as the basin fills. So we have our posts holding the coir baffles spaced about evenly across the basin. And then at the outlet here, we want to make sure that there's a fiber mat or some kind of matting so that when the water leaves this pipe, it doesn't create an erosion on the back side. So we have some different options for stapling in all that fabric that's on the dam that prevents the dam from eroding. So most people are going to use those landscape staples. So we have another feature here, the emergency spillway or auxiliary spillway, a lot of different ways of calling it. But in a normal skimmer basin, the same picture, we see we have a cut here, and we've lined this dam. So we want to make sure we don't have any chance of this dam eroding with a lot of overlap. And we already talked about the staples. And then we have this weir. So if we have a lot of rain and this basin fills up, the skimmer can't dewater very fast, then it will start to go through this cut in the dam. So the weir's width here is specified on your plan. So the size of the pipe and the orifice we'll get to on the skimmer, that's specified on the plan, but also the width. So bigger basins or more flow expected will have a wider cut in that dam. Now, if we're temporarily using a stormwater basin, which you see here, as a skimmer basin, then the emergency spillway is actually the pipe that you see here, or it may be this is a concrete pipe, it may be corrugated, and so that's actually when the basin fills up, that's where the water is going to go. That's the equivalent of this spillway. All right, well, let's talk about those skimmers. There's many different kinds that are on the market right now. In most cases, we're looking at the Faircloth skimmer specifically here, but some of them have a pipe orifice right here, and we may or may not want to restrict that. That is to say, on the plan, it'll say use a, let's say, in this case, a 4-inch skimmer, but we want a 2.5-inch orifice. So that means we need to take this plastic plug that comes with the skimmer, cut a 2.5-inch hole with the tool that it's given, and then put the plug in there. And that restricts the flow so that it maintains a pond for 48 to 72 hours. So if we left that just open, then it would drain too fast. So we want to make sure that we follow the plan, and if we're putting in a skimmer that requires a plug of some kind, we cut it and put it here at the orifice. So there's several that are approved for use on DOT projects. This is the Faircloth skimmer, the kind of the original one, made in Hillsborough. They actually have a robotic factory up there. You can tell the Faircloth because they've got this snorkel that you see here, and the snorkel has a piece of tape, colored tape on it, and that tells you what size this barrel is. So that's color coded. I don't know what the color code is, but that way you know. There's also this IAS skimmer, pretty different in the way it works. It has an arm going each side that actually bends down. You can kind of see the bend. And there are holes cut underneath that so the water comes up into the pipe underneath it. So, so these are sized based on how many holes you have. So more holes, more drainage, larger basin. I actually haven't seen very many of those out. The other one you see a lot of is the Erosion Supply skimmer. So that's made in Raleigh by Erosion Supply, and they have sort of a similar concept to the Faircloth skimmer, a little bit different. Notice they have 4 legs, and the idea there was that that would prevent it from sticking in the mud. They also have plugs, as you see here, so you can use the same skimmer on different basins with just different size plugs, and you'll get the drainage that you want. And while we're looking at this, I want to note here that we have the pipe, which we've already seen before. Notice how it's elevated. And we generally do that on DOT projects to create a standing pool, which we'll see in just a minute. So this is the ProDrain 70. Again, pretty different concept. If you look down here on the right, you've got this outer screen that prevents trash from getting in, but inside that, there's a sleeve, this white sleeve, that you move up and down across these slots to adjust the flow. So you look at their table, and if you need a certain flow, you move this sleeve out or up to get flow changes. So kind of a clever idea. And here I want to show you also the standing pool. So we've got that pipe going through the dam at a foot above the bottom of the basin. So we have about a foot of standing water here. Why is that? Well, there's a lot of reasons. One is that's the dirtiest water. So you picture we fill up the basin, sediment's constantly settling. So at the bottom, that's the dirtiest water. And so in this case, we're going to leave the dirtiest water in the basin, let it settle some more before the next storm. Secondly, having a standing pool actually increases the efficiency of the basin. So when water comes in filled with sediment, it hits a standing pool, and that actually acts as a brake. It slows the water down very quickly, and it drops out a lot of sediment that way. And then thirdly, if for some reason the skimmer is not on rocks, it will end up floating and it won't get stuck in the mud. So we have quite a few reasons. Also note here we have a rope. So all skimmers are going to need to have a rope attached to them so that if and when this screen gets clogged, then we can pull it off to the side. So make sure there's a rope that's staked off to the side. This is the Marley skimmer. Unfortunately, this has been changed quite a bit, and I don't have any newer pictures of what it looks like now. They've changed it quite a bit. I think there's a curtain that's sitting down below it now, and some other changes in the way they function. But at least the way they used to function is these are weights that would push the pipe down, and the water would come up underneath right from there and end up here and go out through the pipe on the top. And you can see we end up with sort of a swirling toilet bowl kind of motion. But that may be different now, I don't know. So we need to make sure they're properly installed. We understand that if they need a plug, that we get that plug in there before we walk away from our installation. Okay, so give me some of the benefits of a standing pool in the sediment basin. I listed a few. So, dirtiest water in the basin, slows the first flush, keeps the skimmer off the bottom, none of the above. Hopefully everybody said all of the above. So a lot of benefits to that. Now, I will mention some people ask, I guess, if there could be a problem with mosquitoes having a standing pool of water. And the answer is generally no. And there's a couple of reasons. One is they don't like to be out in these open areas where you generally have these basins. They like to have a lot of vegetation around. And secondly, the water in the basin actually is not very conducive to them laying eggs and having larvae because the water is dirty and it also gets very hot. We've measured temperatures of 110 degrees or higher in the water in the summer, so that's going to cook anything that's trying to live in there. So in my experience being around these basins, I've never had mosquitoes be an issue. All right, so the spillway on the dam safely removes water during high flow events. True or false? All right, that's the whole point of that spillway. So we have a rope tied to each skimmer. Why? We want to keep people from stealing it, maintain the water level so inspectors can check it, or to clean it periodically. All right, so we're wanting to be able to clean that skimmer. Here's an example. We were walking by this basin and noticed there was no flow, even though it was full. And we went over and got the rope and pulled the skimmer over to the side, and you can see that they had a big storm, a lot of straw washed into this basin, and it completely clogged that skimmer so that there was no flow leaving this basin. And so as a result, the only flow that was happening was going across the spillway. But so that's why you need to have that rope so you can clean the skimmer. Now, kind of a variation on the skimmer basin is a tiered skimmer basin. So picture that we have a fairly steep slope. Here's an example here. And if we actually made this one big basin, then the wall on the uphill side would be like 20 or 30 feet high. And that's just too much. So one way we can deal with that is to tier the basin down the slope. So here we have the first cell where we're bringing in the water from the ditch in our 12-inch corrugated pipe. We've got a couple of baffles, and then this will fill up and then spill over into the second tier where the water will go through a baffle and then our skimmer. So this is a cutaway. You're basically looking at a skimmer basin that's been cut in half with a dam. So we've got our spillway here. And, I'm told that we don't use a 12-inch pipe very much anymore. We just use a spillway. So this would be a lined spillway, allowing the water to go through the middle here and then down safely into the second basin. I've seen as many as 4 of these tiered down a steep slope. And again, the staple options. Now we often joke that the best way to handle stormwater is to infiltrate it, but that's very hard to do in most parts of the state. However, there are parts of the state that have very sandy soils, and water will actually exit them through the bottom instead of over the top. And in this case, in those areas, we can put in infiltration basins. So it's exactly the same as a skimmer basin, except there's no skimmer. So you see we do have a dam here, and we've lined it so it won't erode, but we've got our baffles, and we really expect this is probably groundwater in between stormwater events. And once the basin starts to fill up, then it will just spill out into the sides through the soil itself. So we don't expect any discharge out this end. And I want to point out here, when we get to baffles, one thing about baffles is they need to be level. And so here's a good example. They're tipping down on the sides. We need these to be level. Bird's eye view and cutaway of a infiltration basin. So it's just a skimmer basin without any kind of a skimmer, essentially. And there's another cutaway. We've got our 5-foot stakes, 3 feet above and 2 feet in the ground, evenly spaced. This is an old structure that we used to use a lot, and now I don't think we use it too much anymore. But it's a sediment dam type A, which has the large stone, the type B stone. And then we cover that up with the 57 stone to slow the water. So for large drainage areas, this is a pretty serious structure here that can handle the flow. Notice how we have a weir. We need to have that at all times when we're getting flow through these dams. So again, a little drop here where the weir is, and we've got the large stone and 1 foot of the 57 stone on the front. So that's the sediment dam type A. And then the type B is for smaller drainage areas. And here you can see we actually have baffles installed. We have the smaller rocks of the type A rock is used here as a structural stone. And then we've got the 57 stone. I hope everybody can repeat after me, 1 foot depth of the 57 stone to slow the flow and get sediment to settle out here. All right. And another cutaway of that dam with the 57 stone on top of it. And again, we don't see very many of these, but you will see them occasionally. All right, this is a slide I want you to burn into your memory. So finally getting to talk about these baffles that I've been mentioning all through here. These are coconut fiber. But here's why I want you to remember these slides, because this basin is a perfect basin, as much as any basin can be perfect. So here we've got our corrugated pipe bringing the water safely in. Notice how we've got these stakes on both sides of the pipe to keep it in place and keep it from pulling out from the dam here. We've discharged the water onto a safe stone pad. The sides are cut away to about a 2-to-1, and they're all lined with the Excelsior blankets. And hopefully there's grass that'll be growing up through that shortly. And then we have the baffles, 3 of them evenly spaced. And then we go to the other end and we look and we see our Faircloth skimmer that's been installed on top of a rock pad. And we have, actually in this case, they put rope on both sides of it, probably to keep it from floating to side and keep it on that rock pad. So this is what every skimmer basin should look like. Just kind of remember that. Okay, so now back to the baffles. So we're going to use steel posts, as you see here, just like in silt fence. They're going to be on a 4-foot spacing instead of the 6-foot. We're going to use 700 gram per square meter coir or coconut matting. Now, this matting is made in either India or Sri Lanka for the most part. And they're on metric, so they sell it as metric. And so it's either going to be sold as a 400 or 700 or 900 or a 1200 grams per square meter type of material. So you can imagine the higher the weight, the more material is in the making of these mattings. So we're going to put a wire across, and we're going to fold this coconut matting across the wire so that we have a double layer here, and then staple it down at the bottom, and then use zip ties to hold it to the wire as well as the posts. Again, if we were in the field, we'd be taking a look at these installations. So here's a couple of diagrams of the installation. So here's our posts on 4 feet. In this case, a post was used to bring the fabric over to the side, or you can just stake the wire, either one, and make sure that it goes level or up in this case. But you don't want it to drop down. If it drops down, then when you get high flows and high volumes, flow will go around instead of through the baffle. And you really want all the flow to go through that material. At the bottom, we want to make sure the water doesn't go underneath it. So when they make these, they're made in 2-meter wide rolls. Again, they're on metric, so that's 6.5 feet. And remember I said this is 3 feet, so that means you end up with a couple of inches on both sides, and you staple those down so that water can't get underneath the baffle. This was an interesting shot of a case where they couldn't get the posts all the way down 2 feet because they ran into rock or something. And I thought this was pretty clever. They decided to improvise and supported the baffle anyway. So whatever you need to do. All right, so I'm going to show you why we're using these porous baffles with a couple of videos. So this is a tank I made in the laboratory, and I'm going to introduce water with dye, as you see here, to show you the flow. So pretend that this is muddy water coming into the basin during a stormwater event. There are no baffles, and so we've got a lot of turbulence all the way to the exit. Okay, so picture trying to settle when you got all that turbulence. So now we put in a baffle, just one, and we'll see what happens. We're going to start out with all that turbulence, just as we had before. But what happens when that muddy water reaches the baffle?
Oh, that's good. Mm-hmm. Oh my, that's really good.
I don't know if you all can hear that, but we were pretty impressed in the lab with what it looked like. So here's the thing you're seeing is the water that has this dye is a little bit heavier than the water that's clear. And so as it comes through the baffle, there's so little turbulence on this side, it actually settles because it's a little bit denser. All right, so that's what we're doing with our baffles. We're trying to spread the flow and take out the turbulence. And here's a full-scale shot of that. So again, we're introducing the dye. Again, this would be what you'd see if we were doing it out at our Lake Wheeler field lab, typically. And so a lot of turbulence over here, as you would expect. But over here, you notice how we now have the turbulence removed and the water is just moving sort of straight forward in these fingers. And that's great for settling. That's the key, is we're trying to take out the turbulence so that we can settle the heavier particles. And then we get through the second baffle, and then you really see that effect. Okay, you see we're spreading the flow and taking out the turbulence, and then look here. Now you can see those fingers and how there's just no turbulence at all. And that's perfect. So between the removal of the turbulence and spreading the flow and taking water off the top of the water column with the skimmer, we can get these basins to take literally 99% of the sediment out of the water coming in. We've measured that on real construction sites. So hopefully everybody understands why we're putting in baffles and skimmers. So porous baffles, after you've seen those videos, hopefully you can say they help by spreading the flow and reducing turbulence. All right, so moving on to other types of impoundments for dropping sediment out. We've got the earthen dam with skimmer. So this is essentially a skimmer basin, but there's no dam up at the other end. There's no wall of soil or whatever that you'd see on a skimmer basin. So this is on a gradient. Say this is really a ditch, and we're just going to create a little sediment basin in the ditch line. Everything else you see is going to be just the same as a skimmer basin. We got the baffles, skimmer, the rock pad. We've got the pipe elevated a foot off the bottom, and we've got the emergency spillway, and the dam is all covered up with the geotextile. So pretty much a skimmer basin without a upper wall. So we saw a picture earlier of how we can use a stormwater basin as a skimmer basin temporarily. So the concept here is pretty simple. We have a lot of places where the drainage from the roadway has to be controlled, and so they would build these big storage ponds or stormwater ponds, and these are intended to hold the water and slowly release it into the stream safely without eroding the stream. Well, you can build these ahead of time as the construction of the highway is ongoing, and use it temporarily as a sediment basin. So in this case, we have a concrete riser. These risers almost always have what they call a weep hole, which is a hole down near the bottom. We can attach our skimmer to that and put in our baffles, and voila, we now have a skimmer basin. And remember, again, this is now the spillway, or similar to the weir in the dam. And here's a metal riser, same concept. We've attached the skimmer to the weep hole. And here's our aerial view where we've got the spillway here, the concrete riser or metal riser, skimmer, baffles, etc. We do have on a stormwater basin, you're going to have some kind of emergency overflow spillway, which we won't have with our temporary basins. And a cutaway view. One thing to point out is I didn't know this until I started working in this business. These risers have to be anchored in concrete, otherwise they will actually float and pull this pipe up and create a big problem. The other thing that I learned is that there has to be some kind of a device on this pipe that prevents water from moving along the pipe. So a collar that keeps water from flowing along the pipe. So a lot of neat things about these basins. All right, so let's say we have to do some work that's actually in waters of the state. In this case, there's a number of things we need to do. First of all, remember, anytime you're working in wetlands or waters, you have to have a permit. So all these that I'm showing you here would have been permitted. They would have had a permit from the Corps of Engineers and the Division of Water Resources. So here's a simple case. So picture that our highway is going this way. We have to cross a stream. So we're going to build a culvert. Well, in order to build the culvert, which you see here, we need to get the water out of the way so we can build it. So we're going to put a dam in right there. And in this case, we're going to put a pump into the stream and pump the water around the work area, release it safely. Notice energy dissipation, put some rocks here so we don't erode the bank, and get it back into the stream. So this is water that's never been touched by our project, so we can just pump it and release it. However, inside the project, we may get groundwater leaking in or some of the stream, and so we may have to pump water out from where we're working. Well, that's in our work zone, so now we got to put it through some kind of a treatment. So here we've got our pump, we're going to pump it out. In this case, it can be either a sediment bag, which we'll talk about in a little bit, or a little stilling basin, a miniature sediment basin. So this is one option, pump the water around your work area. Another option is to put a pipe in the dam and run the pipe straight through the work area and out the other side and just work around the pipe. So that's another option. Or you can take that pipe and move it to the side and dam your flow and move the flow through the pipe and then out back into the stream. And then lastly, what I've seen most common is that you can dig a new channel, line it with some kind of fabric, and make sure that it's secured, and send the flow out back into the stream. And that way you can build your culvert and then take the dam out and let the flow go through the culvert. Another situation is where you have to get to the other side of the stream just temporarily, maybe to build some bridge supports or something, but you don't need to have a permanent crossing. So in this case, we're going to use a temporary crossing, which consists of this fabric that's put down in the stream bed, and then a pipe to allow the flow to go through, and then the Class B stone, the large rock, on top of that, and then we put a 57 stone gravel on top of that for our travel lane. So here's our diagrams, bird's eye view and cutaway view. So we're going to fill that up with the rock and put the 57 stone on top. So once we're done with that, we can pull this material out, dig out all this stuff, and then pull up our fabric, and the stream will essentially be undisturbed, which is why this is a good practice. There's some other things we can use either to divert flow or to keep water away from a work area. So here you can see some sheet pilings. Here we've got some sandbags that are used to hold the water back from a work area. And these can also be used as these dams. What we were talking about before was earth covered up with some fabric. And in this case, we could put in sandbags or sheet piling, or put some stone in with plastic over top of that. So a lot of different ways we can stop the flow and move it into our diversion system. All right, so I mentioned briefly that if you're pumping dirty water from inside your work area, you have to put it through a treatment system. So there's a couple of options we use for the most part. One is a stilling basin, which you see here. We have the fabric, and everything is the same for our coir baffles that we were talking about before. Difference is we don't have a skimmer, and we have a rock outlet. So that's a little bit different than our skimmer basin. Bird's eye view, so we're pumping the water and making sure that that is also released so it doesn't erode the inside of that stilling basin. And then we have an over excavation, so it's a foot deep here. So the water has to rise up a foot and then goes out through the stone. So that's our stilling basin concept. So it's essentially a simplified version of a skimmer basin. The other option is to pump it into a sediment bag. So these are geotextile bags that are constructed to take flow and filter out a lot of the sediment before the water is released. So this is generally used in areas where you just don't have room for a stilling basin. So here you can see the pad of 57 stone that's been put out, and make sure this area is level. That's really important, otherwise that bag might roll. Another option is to use some pallets as something to lay that bag on. And what we're trying to do with both these cases is create a stable environment for the bag, but also allow the bag to drain out the bottom as well as the top and sides. So there's a couple of reasons for that. The other thing you want to be thinking about if you're using these bags is, how am I going to remove that bag once it's full of sediment? And I can tell you that it's a afterthought for a lot of people, and it's always a problem, because you really can't lift that bag. The material will rip if you try to lift the bag. So you need to put some ropes or some kind of material underneath it that can handle the weight, that you can pick it up and move it, and generally people bury it on the site somewhere. I have seen them actually put one of these bags in a truck itself, so that when it's full, they can just cart it off and put it somewhere. So here's those diagrams again. We've got our bag out on the 57 stone, and as always, before you put stone down, we have to put down a geotextile. So you can see that lining right there. Otherwise, the stone will just get pushed into the ground. We want to make sure that this flow gets back to the stream without causing any erosion as well. All right, so that was all our practices that we use. And I mentioned earlier that there's a couple of resources out there if you want to have sort of a reference. These are some of those. A lot of the diagrams came out of this booklet here. And this is some examples of what you see inside that book, which is available. You can download it. You can download this 4.1 section. It's pretty big, but it's got all these diagrams. It's a great resource, pictures, tips, definitions, where you use it, and some of the problems you might run into. It's got all the diagrams we've been seeing today. So lots of resource there. So you just want to go to the connect ncdot.gov, and or you can just Google it. You'll get there eventually. Roadside environmental, and look at soil and water, and there's our manual right there. If you love drawings, you can also download these drawings that we've seen as well. So I think those are in one of the handouts that Joni sent, these drawings. So most importantly, our BMPs are installed correctly, which is why we went through this whole section. Look at the drawings, make sure you're taking topography into account, that you inspect them often. So this is requirements that we inspect once a week or after a 1-inch rainfall event. Generally, those are the level 2 people, but this is important. And then we maintain them so they're actually working. And remember I said, if you have a half of any device full of sediment, that sediment has to be removed. So you don't want to wait until you have a failure.